Hello everyone, welcome to Applied Chemistry Tutorials. Today we are going to discuss about mean deviation, variance and standard deviation. Let us start with a brief introduction. For any chemical and physical experiments, we generate data, and thoughtful understanding of this data helps us to properly conclude our observation. We know that experiments lead us to observations, and from observations we can have conclusions, but there are two hidden steps between observations and conclusions. From observation we get lots of data, and this data needs to be analyzed to get proper conclusions. For any statistical analysis we calculate central tendency, which can tell us where the data points are centered, and also we calculate dispersion, how these data are scattered around a particular central tendency, which is mean, median or mode. So we have discussed calculation of mean, median and mode in our last video, and today we are going to talk about the dispersion. Measurement of dispersion. So there are four major ways to measure dispersion of a data: range, mean deviation, variance and standard deviation. So let us take an example to understand the dispersion of an ungrouped data. We are keeping the same example from our last video so that the viewers can understand it easily. Consider two boxes A and B. Each contains 10 small bottles of diluted hydrochloric acid. Volume in milliliter in each bottle is given as follows: box A 5, 7, 3, etc. For box B 5.5, 3.5, 3, etc. Now we need to find out the range, mean deviation, variance and standard deviation of this data for two boxes. Let us start with range. Range of a series can be given as maximum value minus minimum value. So for box A and box B, we can easily find out the maximum and minimum value. And for the given example, for range of box A, we can find out as 7 minus 2.5 equals to 4.5, that is 4.5 ml of diluted HCl. Similarly for box B, the range is 6 minus 3, which is equals to 3, that is 3 ml of diluted HCl. So it is to be noted that determination of range is easy and it can give us some idea of variability, but it will not tell us about the dispersion from a central tendency. So to overcome this issue, we have introduced mean deviation. Say in a given dataset x1, x2, x3 up to xn are the values of n quantities, and we need to find out the mean deviation from a central tendency A. Then we need to follow the steps. Step 1, we need to find out the deviation of each quantity from A, that is x1 minus A, x2 minus A, x3 minus A up to xn minus A. In step 2, we need to find out the absolute values of all the deviation, that is modulus of x1 minus A, modulus of x2 minus A, modulus of x3 minus A up to modulus of xn minus A. And in the third step, we need to find out the mean of these absolute values of the deviations. So for our given example, let us calculate the mean deviation about mean. So the central tendency here is mean, that is A equals to x bar. So in the given example for box A, the mean of the data can be calculated as x bar for box A equals to 5 plus 7 plus 3, that is the data we can have originally, divided by the number of quantities, which is 10, which is equals to 4.2. So we can say that the x bar for box is 4.2 ml of diluted HCl. Let us now calculate the mean deviation about mean. So mean deviation about mean can be given as 1 over n summation of I equals to 1 to n modulus of xi minus x bar. So let us now calculate the mean deviation about mean step by step. In step 1, first we calculate x1 minus a here, which is x1 minus x bar, that is 5 minus 4.2, which is equals to 0.8. Similarly x2 minus a equals to 2.8. And in the similar way, we can find all the deviations, and that can be given in the newly formed data set. So now in step 2, we need to take the absolute values of all the numbers that we obtain in step 1. So for 0.8, the absolute value will be 0.8. For 2.8, it will be 2.8. For negative 1.2, it will be 1.2, and so on and so forth. In step 3, mean of the values obtained in step 2 that needs to be calculated. So mean deviation about mean is summation of all the numbers that we obtain in step 2 divided by the number of quantities 10, which is equals to 1.24. So therefore, the mean deviation about mean is 1.24 ml of diluted HCl. Similarly, we can calculate the mean deviation about median if we consider A as median. It is important to calculate the absolute values, otherwise the mean deviation from a central tendency would become 0, which we can clearly see from here. If we don't take the absolute values and sum the all original values that we obtain in step 1, then we can definitely have 0. 0.8 plus 0.2, 0.8 minus 1.2 minus 0.0.2 up to this, it can lead us to 0. So there would be no meaning to calculation of mean deviation from a central tendency. Now let us talk about variance. So mean deviation from a central tendency can sometimes lead into erroneous result, because algebraic treatment of absolute values can be wrong sometimes. The median sometimes can be misleading due to very high degree of variability. So mean deviation about median would be unscientific. Also, the sum of deviation from mean and sum of deviation from median are not equal, so that is also unscientific as well. So to avoid these issues, variance can be a way to represent the dispersion, which can be given as 1 over n summation of I equals to 1 to n xi minus x bar whole square, which is a non-zero positive value. We can clearly see this is a summation of all the square terms, so this is absolutely a positive value. And similarly, we can easily prove that this is a non-zero value. If we consider them as 0, then each of the term x1 equals to x2 equals to x3 all will become equals to x bar, which is not possible, and so this should be definitely non-zero positive value. So clearly the negative terms are avoided here by squaring the terms xi minus x bar for I equals to 1 to n, rather than just taking the absolute values. So for the given example, let us calculate the variance for box A. So these are the given data set for box A. So in step 1, we calculated x1 minus x bar, which is equals to 5 minus 4.2 or 0.8. Similarly, x2 minus x bar is 2.8. Similarly, we can have all the other deviations from all the given data. In step 2, we will take the square of each of this term, and x1 minus x bar square will give 0.64. Similarly, x2 minus x bar square will give 7.84, and we can have this number for all the data for box A. And in step 3, we'll sum them up and divide by number of quantities, which is 10, and we'll get the number is equals to 2.01. But in this number, we cannot have a particular unit which has its physical significance, because this number is a summation of the square terms. So that means it will be as milliliter square, which has no physical significance. So to avoid this, we have introduced standard deviation. So for standard deviation calculation, the main point was that for variance we cannot have such a unit which has any physical significance. So to avoid this, we need to we can take square root of the variance which is defined as the standard deviation. So therefore the standard deviation sigma can be given as sigma equals to root over of 1 by n summation of I equals to 1 to n xi minus x bar whole square. So in the given example, the standard deviation can be calculated as sigma equals to root over of 2.01, which is the variance, equals to 1.42. Now this has a proper unit with the physical significance, and we can say that therefore the standard deviation is 1.42 ml of diluted HCl. So the standard deviation formula, we can see we have one summation of squared terms, and which all are divided by the number of quantities n. So why n is important in this formula? To understand this, let us consider two different data set 1 and set 2, which have two different ranges. And for set 1 we have a larger range, for set 2 we have a shorter range. In set 1 we have only 5 data, in set 2 we have 10 data, so n equals to 5 here and n equals to 10 here. So from visual inspection we can clearly say that set 1 is more scattered and set 2 is less scattered. But it may be the case sometime that summation of I equals to 1 to n xi minus x bar square, which is this term, for set 1 is less than that of set 2. So we can have misleading information from this. For this, now we can, if we divided this number with n or number of quantities, then it can give us the sigma for set 1 will always be greater than that of set 2 due to the presence of this n. So the standard deviation is the proper representation of the dispersion. Now let us talk about the normal distribution. So here we plotted probability distribution function fx versus the mean x bar, and then we have added which is given as the topmost point, and then we added the standard deviation with it, x bar plus sigma, x bar plus 2 sigma, and x bar plus 3 sigma. And in the other way we have subtracted the standard deviation from the mean, so x bar minus sigma, x bar minus 2 sigma, and x bar minus 3 sigma. So this probability density function tells us that the 68.2% of the data in a given data set will fall between the range of x bar minus sigma and x bar plus sigma, whereas 95.4% of the data will fall in the range of x bar minus 2 sigma to x bar plus 2 sigma, and 99.7% of the data will fall between x bar minus 3 sigma to x bar plus 3 sigma. So for the given example, for box A, we have already calculated the mean to be 4.2 and the standard deviation is 1.42. So we can easily now calculate x bar plus sigma, x bar minus sigma, and all these numbers. So this range is given by it should almost 68.2% of the data should fall in this range. Now let us take a look in our example. So we can say that except these three values, all other 7 numbers fall in this range. So we can say almost 70% of the data fall in this range, and these three numbers 7, 2.5 and 6 fall in the range of x bar minus 2 sigma and x bar plus 2 sigma. So that will make up the whole 100%. So here it's showing the 95.4% of the data, which is very close for this context. So this probability density function can be given as fx is equals to 1 over sigma root over of 2 pi multiplied by e to the power minus half multiplied by x minus x bar over sigma. And this probability density function will be more accurate for a larger data set. So when n is very large, we can have almost this 68.2% number for this region, 95.4% for this region, and 99.7% for this region. So this is all for today. For more videos, please stay tuned with our channel. Thank you.